I'll move then to the example of how to deal with a problem that has unsymmetric cross sections. In this particular problem, it is stated that there's a uniform cantilever beam that has an angle cross section. You can see the cross section here is similar to the example problem I did earlier on a bracket that had very similar dimensions. It is subjected to a moment about the z-axis right here, and that's 500 newtons per meter. You can see here by the right-hand rule that the z-axis is going into the page, and so mz is acting in the same direction, and that's why it's positive. There's no applied moment about the other axis, about the y-axis, so my is 0 in this case. The area moment of inertia of the whole cross section is given to you. So you're given that's the moment of inertia, and is given relative to the y0 and z0 coordinates given here. So these moment of inertia are known, and the product moment of inertia is given as 0 for this coordinate system. And so the question being asked is to determine the bending stress sigma xx at point P. And they also want us to calculate the orientation of the neutral axis and sketch it on this cross section. So when I look at the inputs, we want to remember that the flexure formula is given by this formula here, where the inertias are about an axis, z or y, or the product moment of inertia, but they're at the centroid, c. And so we will have to then determine the moment of inertia at the centroid, given that I know them at a different location, which is here, these numbers here. So I know that moment of inertia, that moment of inertia, but we'll have to find this one and this one. So the first step is to determine where is the centroid. So we can divide these pieces into two. So I have, two different parts here. And so I'm going to calculate the moment of inertia, the centroid first. I'm going to use this base as a reference point to figure where the point C is, the centroid. So when I look at this particular piece, we can see here that the area of this piece is 10 times 100. As you can see, the red dash put it here, so that's the part I'm looking at. That's part one. And you can see here that you can see here that the origin is going right through the centroid. So the height z is 0 for that part. So that's 0. And then I have to calculate where the centroid of this little piece is, and that's about here. So let's see if we can calculate that location. You can see that if this is 100, that's 10. Therefore, this distance here is 90. And 90 divided by 2 is 45, which is the height that we're looking for. So yeah, so if this so the area I'm looking at here is 90 times 10. And then I have to find the distance between this point and the centroid here. So this point is to this dash 9 is 5. And 5 plus this distance is 45. That's 50. That's this number here. And now I know the area of the whole thing. So that's easy. That gives me that the centroid is 23.68 and it's at this location. So I can translate this axis to this axis here. That's where the centroid is. And it turns out that if you calculate it for y bar, the same procedure, you also get 23.68. You can now determine the moment of inertia about y, which is this axis, for example. I am given what the moment of inertia is about this y-axis. So I know what that value is. And it's given to me for actually the whole part. So in this case, I'm not looking at individual parts. It's giving me the moment of inertia for the whole cross-section. So I know that number, which is, you can see it is given to me as 286. So for the whole cross-section, the moment of inertia by y is 286. And so that means I have to look at the area of the whole cross-section, which is 10 times 10 times 100 plus 90 times 10. That's the denominator here. But now I have to use the distance for 23.68, which is the distance between this point and that point. And the parallel axis theorem then will then allow me to calculate the moment of inertia about y. And I get this number. It turns out that about the z-axis, you get the same number as well. You can also repeat the process for the product moment of inertia. We were giving it a 0 for the whole cross-section about this reference axis, z0 and y0. I know the area again, which is the whole cross-sectional area of these two pieces together. And I have dy times dz, one of them negative and one of them positive. When you do multiplication, you now get the product moment or inertia. So now I have all the properties relative to the point C, which is where I needed it, where the stress is actually 0. So now that I'm able to do that, since the moment applied is my is 0, only mz exists, we can now calculate so I actually corrected this. There was an error. My is 0 per the problem statement. You can see that here. No my is given. It's telling us that only mz exists. So that was an error that I have fixed. So mz is 500. I know this number. That's that number. And then it's asking us what is the stress at point P right here. So relative to the centroid, I have to figure out what distance that is, the coordinates of that point relative to the centroid, and I get that z is 0.02864 relative to this point. I can then calculate mz is 500, and then the moment of inertia Iy is 1.80 times 10 to the minus 6. And then I have that y coordinate that goes from this point to that point, obviously in a negative direction. And that also gives me a number of minus 0.07132. I have these calculations at the bottom because I already did them earlier. And the stress at point P then is calculated 23.16 megapascals. The final question of the problem is what is the angle of that neutral axis, which should be measured by z. So that's the formula for that. You can see that this and my is 0, so mz cancels out, and then you get just the ratio of the inertias. And when you do the calculation, the phi angle is 30.5. And what that means is a neutral axis, that stress there is 0. The farthest point away from the neutral axis will give you the highest stress. Uh, I have the feeling that maybe this point right here, but you may want to check. But you're looking at distance farthest away from the neutral axis is where you'll get the highest stress. That concludes this particular lecture.